Sure. As Steve and I prepared our activities for this evening, we looked at the Common Core State Standards, specifically around the area of transformational geometry. Mike, if you could show those standards that we're looking at, this document is going to be shared with you after our evening together. But you can see that this idea of proof using transformation, rigid transformations, a lot of new terminology that may or may not have been part of your geometry curriculum prior to this point. We're optimistic that the activities we'll be looking at this evening will help you assess where your curriculum is and how you move into this Common Core era with this topic in your geometry curriculum.
Thanks, Bill. At this point, Steve is going to discuss our expected outcomes. Steve?
As you folks can see on the screen, we've got several things that we hope to be able to accomplish by the time this webinar is over. We're going to look at an activity that will assist us in creating our own definition of a rigid motion. We'll let the students do a creation and actually produce their own definition. Then we're going to do another activity in which we investigate the properties of rigid motions in an effort to identify those. And finally, we hope to demonstrate an activity which illustrates the first step in the use of rigid motions to establish congruence in a way that's really a little bit different than what we have traditionally done in our curriculum. And finally, at the end, we'll have an opportunity to talk about staying in touch through social media and upcoming events.
Thanks, Steve. Bill, go ahead and share your desktop. And as Bill is doing that, you'll notice that the chat window and the Q&A windows, which had been on the right side of your screen, whenever Bill shares his desktop, they'll be replaced with a green floating toolbar. And so you'll be able to still locate that chat and Q&A window if you just hover your mouse underneath that green floating toolbar. Bill, it's all yours.
Great. Thanks, Mike. We're going to begin this evening by looking at some definitions of transformations. Again, I would remind you that you'll be receiving these documents at a later date, but feel free to follow along this evening as you find appropriate. We see here a set of instructions. We're going to be looking at a triangle ABC, and we're instructed to use our points and lines tool to construct the vector V. Then using the transformational toolbox, we're going to find the image of that triangle under a translation through our vector that we create. Using some of these tools may be new to you as a user of TI-Nspire. But to create a vector, I'm going to use my points and lines tool. This is what we were instructed to do, create a vector. So I'm just going to create a vector here. Notice in the top left-hand corner, I have a tool icon that indicates that my vector tool is active. We were then instructed to transform our triangle ABC by a translation. One of the many nice features of TI-Nspire is that when I've selected this tool, and I'm not particularly sure about how the tool works, if I hover over this tool icon, it gives me this quick instruction that to perform this translation, I need to click on the object that I would like to transform, and then tell it what vector I want to use as my translation vector. So I would like to translate triangle ABC by this vector. Right away, I see my image triangle showing up here. I'm going to label my image triangle. This will be my point A prime, C prime. I'm just going to work my way around the figure. B prime. If I don't like where the labels appear, I can control that. And of course, the power of interactive geometry is that this is not some static drawing that we have, that this is active. If I were to change my translation vector, immediately my image triangle changes in real time. So I can see the results immediately. The key here now is how are we going to define this transformation called a translation? If I were to look at the segment connecting A to A prime, for example, B to B prime, C to C prime, what might I want my students to conjecture about those segments? What might I want them to conjecture about the length of those segments? What about the slope of those segments? These are all things that we could confirm using our geometry tools. I can measure the lengths of each of these segments, B, B prime, A prime, and I'm just going to store these measurements here off to the side so I kind of manage my screen activity here. How would they compare to the length of my vector? Again, if I change the length of that vector, interactively, I see the change affected by the image triangle. I can also measure the slopes of those segments. So I see that the segment connecting the pre-image to the image is equal in length to the vector and also in the same direction. Those segments are all parallel to each other. How might your students define this transformation? Always good to continue to think about what questions you would ask. What about the pre-image triangle and the image triangle? What might be true about those triangles? Let's measure the angles. Let's measure triangle BAC.
Bill, I think Pamela had a good question I just wanted to raise.
Sure.
She asked, how do you define the vector for a geometry student?
I define a vector as giving distance and direction to the motion. The distance being the magnitude of the vector and the direction being the slope of the vector. Steve, if you want to add a comment here, feel free.
No, I think that actually pretty well describes it. What we want to talk about is that a vector is a directed quantity. And a vector has, as you indicated, two properties. It has a direction and it has a distance. It looks like a line segment. It has the same length as the line segment, but it has a direction indicated in this case by the arrowhead.
Right. And I would point out that when you're using this transformation tool, you can actually perform a transformation, the translation along a segment. As Steve just mentioned, you know, if I translated along a segment and clicked on one endpoint of the segment and then the other, that would define the motion. but I like using the vector because the visualization of the arrowhead helps the student visualize the motion as opposed to remembering the direction that they selected the endpoints of a line segment. Pam, if that doesn't answer it for you, feel free to send back another question. Mike, thankfully, is monitoring the chat for us. So as questions come in, please feel free. We'd love to make this as interactive as possible, but with a class size of 124, we're somewhat limited. So let me continue measuring, and now I'm going to measure that image angle B prime, A prime, C prime. And we see readily that those angles are congruent. We could also measure the length of the sides of the pre-image triangle and the image triangle. Asking our students then, what is true about these two triangles? I don't think it would be too hard for my students to conjecture that the image triangle is indeed congruent to the pre-image triangle.
Steve, Deborah had a...
Go ahead, Mike.
Sorry to interrupt. I think Deborah had a nice comment as well. She mentioned that vectors are important in 3D imaging, so students relate well to that in terms of, say, video games.
Thanks, Deborah. Very good.
Yeah, that's a good comment, and of course our people that are taking, our students that are taking physics will be very familiar with the notion of vector also.
I think Pam was right. For many 10th grade geometry students, this may be the first time they encounter that word, vector. So a little bit of explanation here would certainly be appropriate. Steve is now going to help us through another transformation.
Okay, thanks, Bill. We're going to look at, and of course, one of the goals, I think, and this has always been my philosophy, is to attempt to get the students to define a particular, to come up with their own definition. In this particular example, the definition of a rotation. I've found in the past that if students create their own definitions, then they own their definitions, and if they own them, they have a better chance of remembering them. On page 2.2 in this TI-Nspire, and I'll remind you again that you will be able to download these after the webinar when you get the recordings. And then you'll be able to follow these particular things too. And I'm going to create, in order to do a rotation, I'm going to create a point and I'm going to label it P. And this point is going to be the center of our rotation. And now what I want to do is I want to rotate the triangle ABC about point P through the angle that's listed up there as a driver. Now there's a purpose for that. And notice if you click on the tool tells you exactly what to do. I'm going to caution you to be careful about that because there's a little nuance that's different when you rotate a point, but we won't get into that right now. I'm going to grab the open circle, which controls the size of the angle, and I'm going to move it. And what you'll see as I move it, then the image of the particular triangle changes. All right. And you can see if the angle is 0 degrees, then it hasn't moved at all. Now I would like to label at least a couple of the points, and it's important, obviously, that we label each point with its image. Now this point is B prime because it corresponds to B, and this point is C prime, which corresponds to C, and this point is A prime, which corresponds to A. Now, I want to make a couple observations, and these are the types of investigations we ask our students to do. I'm going to measure the distance from P to B. And then I'm going to measure the distance from P to B prime. And I'm going to make an observation. Maybe it's a coincidence. I'm really not sure. Let's move that open circle and change our figure and see what happens. So it appears as though the distance from the center P to a point and the distance from the center P to the image of that point is the same. Let's test that out. Let's measure the distance from P to A. And let's measure the distance from P to A's image. And what do we observe? Now, one of the things we were going to try to do in this webinar was to try to get a little more interaction from our participants. Now, I believe, if I'm not mistaken, on your screen, there's a place where you can raise your hand. All right, so if we ask a question and you want to raise your hand, feel free to do so, and Mike may choose to unmute you, and we'll all be allowed to answer that question verbally.
Yep. Do I see a hand raised with Jeff right now?
Yep, I've already contacted Jeff. Just so everyone else who may not be familiar with how to raise your hand, if you scroll your mouse over that green floating toolbar where I mentioned that you'll be able to find the chat and then the Q&A window, you'll also be able to find that participants window. And so if you click on that participants window, I believe it's in the lower left, you'll see a small hand. It looks like some people are raising that now. So if you decide to raise your hand, you also have the ability to lower your hand, which is really helpful for Steve and Bill and I. If you want to answer a question, feel free to raise that hand, and I'm going to be unmuting some people in the near future here. But if you don't get picked, then maybe you can just lower your hand so I know who to pick for future questions.
We've got an interesting question in the chat. Lee has asked, could we measure the angle A prime? And it's not unreasonable. That's what's nice about this technology. The A prime, the image, the angle formed by the point in its image, and P is the vertex. And what do we observe? Lee, what do you observe? What if we moved the open point? What do we observe? Maybe we should make a conjecture. I see one answer coming through on the chat.
Yeah, I think we have maybe John, if Steve, if you'd like me to unmute John.
I'm going to have to ask you to do that because I don't see how. Can you do that, Mike?
Yeah, it looks like I'm trying. John may not be connected to the audio, which means I won't be able to unmute him. So I don't know if John's going to be the best choice.
Okay, well that's it. Lee has an answer in the chat. It's been suggested that the measure from A to P, for the measure of angle A prime, is the same as the rotation angle. How could we test that conjecture?
So it looks like,
how about if we, go ahead, Mike.
No, I was just going to mention that it looks like I'm getting a couple hands raised, but I'm not seeing that I have the ability to unmute those people, and so I really think the only issue is that they may not be connected to the audio.
Okay.
John,
well, let's.
John has a question in the chat, Steve. How can you show rotation of a measure greater than 180 degrees?
John, this becomes a philosophical question.
But I'm glad you asked it, John.
Because Bill and I have had a discussion about this. I'm a firm believer of the fact that we don't need to rotate more than 180 degrees because our rotations are either positive counterclockwise or negative clockwise. Now, it's like a lot of things that happen in geometry. It's a matter of the set of axioms that you choose to use. Now, in this particular example, we could easily have drawn that driver, that open driver, with a full circle and made it 360 degrees. But my axiom set prefers angles to have measures between 0 and 180. Does that answer your question, John, I hope? All right, now one of the things we were just talking about is we wanted to make a conjecture, and it appears as though Lee had made the conjecture that the angle formed between the angle A prime is the same as the angle of rotation. Well, one way we could test that conjecture would be to measure another angle. For example, we could measure B, P, B prime. And make the observation that that angle is exactly the same as theta again. Now, we won't take the time to actually do that, but I suspect that if we measure the angle C, P, C prime, we should get the same measurement. That's telling us something very, very important about this particular definition that we're looking for. Right. One thing that I'd like to do in this thing is notice we've only shown the image of a triangle or a triangle in its image. What would happen to other points that are in the plane? So let's make a point and label it Q, any place in the plane. And now let's rotate that point about P through angle theta. Now, this one we have to be careful about because we have to choose the center first. And let's label that point Q prime. And let's manipulate our rotation by dragging our open circle. Of course, everything is moving. Notice that when you do a rotation, every point in the plane moves. Make a conjecture about the angle Q, P, Q prime. And this is an important property of transformations, is the recognition that every point in the plane has an image. We could also measure the distance from P to Q prime. And then measure the distance from P to Q. And observe that that property is the same as it was in our first part of the investigation. And if we measure the angle is the same. Right, now, the screen is getting kind of busy, and when doing this particular investigation, you could move everything to one side, but I'd like to do one last thing with this, and this is the one that turns out to be a little bit surprising. I'd like to find the image of point P under this rotation. So I'm going to pick P as the center. I'm going to do a rotation. And I'm going to pick P as the center. And then I'm going to pick P as the point. and then I'm going to rotate it through the angle that I have there. Now, I don't know if you saw what happened, but if we point at this point, you'll notice it says point, and then there's the word tab. And if you press tab, then it says point P. And if you press tab, it says text, which is the name, but press tab again, and you find point. What that tells us is there's really 2 points there. There's the point P and the unlabeled point. All right. Therefore, we know that under a rotation, the image of the center is a fixed point. That's a little tricky to discover, but it's very important to coming up with the definition. Now we would ask the question, after we've assembled all this information, we would ask the students, how would you define a rotation? What properties would you include? Write, using your own words, the definition of the rotation, the definition of a rotation. Now, in very much the same way as Bill did, and I won't go through this, you'll have the luxury of time when you can do this on your own, but if we move that, if we just observe the triangle and we move that open circle, all right, the one thing that becomes very obvious, and we can get it by measuring the angles of the triangle and the sides of the triangle, that the image of a triangle under a rotation is indeed a congruent triangle. And that this transformation that we've worked on and discovered is actually what we call a rigid motion or a distance-preserving transformation. Now, this activity will continue on and deal with another transformation called a reflection with the same kinds of properties. I think when you sit down with this particular activity and with the notes in front of you, that'll be something that you can actually investigate on your own. So I think it's probably time to move on to the second activity. Bill, do you want to begin the investigation?
Comment, because there's an item in the chat which I do want to just point out because I think it's very important. Emily has said, you said that all the points in the plane are moving, but only the image points are moving. And certainly with this technology tool that we're using, only the figures that we created appear to be moving. And I think Steve would agree there are other things that we might use in our classroom along with TI-Nspire. And for me, it was always a transparency on top of a piece of graph paper. So when I performed the rotation, the students could literally see that the whole plane is rotating. Yes, we've picked out a particular image defined by these 3 points, and then we did. I think that was the power of what Steve had us do with adding this point Q and rotating just the point, so the students could see that we could have done that with any point. That point Q was placed anywhere to get this image Q prime. So indeed, every point in the plane is being rotated.
And to emphasize that, maybe what we ought to do is grab point Q and move it someplace else and see what happens. Right? And Q represents any point in the plane. Now, it's absolutely true that it appears as though we're only creating the image point. But every point in the plane actually has an image, because that's part of the definition, the general definition of transformation. So we move on to identifying transformations.
So this is another activity accompanied by another TNS file where we're going to be looking at identifying a particular transformation. So we're going to see the pre-image triangle ABC and its image triangle A prime, B prime, C prime under a translation through the vector. what we want our students to do is answer each of the following. Is the isometry direct or opposite? The two that we have looked at so far have been direct. We check that by looking at the orientation of the pre-image and the image. Identify any fixed points. As in the rotation, we saw P, that center of rotation, was a fixed point. And is the image of a segment parallel to its pre-image? And is that always true or only sometimes true? So here we see pre-image triangle ABC, and its image A prime, B prime, C prime. Direct. About vector V.
Okay, Bill, you want me to do this one? Are you?
Yep.
Okay. All right. We're going to ask the same kind of questions that we asked before, but we're looking for properties of this particular transformation that are going to help us identify what transformation it is. Now, we know this is a rotation because we've described it as such. But the first property I want to ask is it direct or opposite? And I'm going to answer that question by looking at the name of the pre-image. Now, what I mean by the name of the pre-image is anything you want to call it in any way you want to name it. Let's, for right now, say ACB. If I travel from A to C to B, I've gone counterclockwise. So I say that triangle is oriented counterclockwise. That name is oriented counterclockwise. Now I'm going to look at the images, and I'm going to do the images in the same order. So we went from A to C to B. I'm going to go from A prime to C to B prime. And when I do that, it's counterclockwise. So both the pre-image and the image are counterclockwise. When that orientation stays the same, then we say the transformation is direct. Now notice it makes no difference how you name the triangle. How about if I called it the pre-image ABC? Well, ABC is clockwise. A prime, B prime, C prime is clockwise. They're both the same. So under a rotation, the orientation remains the same and we say it's direct. The second question I asked was, are there any fixed points? Well, based on what we did with our definition, it may not be obvious, but we do know that point P was fixed, but it's the only fixed point. And you could try by using a point Q and moving that point around. So we'd see that only point P is fixed. It's a point that has its own image. So those are two properties that are very useful in identifying a triangle, a rotation. The last of the three questions that we asked was, is a line segment parallel to its image, or is its image parallel to its pre-image? Well, in the particular picture that we have right here, the answer is no. If we move the driver circle, the answer is no. The answer is no. Well, how about if we move it all the way to 180? What do we notice? A line segment and its image are parallel. But that's the only time that they are under a rotation. Now, Bill, if you went back to the translation. All right, and let's ask that same question. Is a segment and its image parallel? is it always parallel? Well, we ask the question, are there any fixed points? So now you're starting to see properties of a translation and properties of a rotation that are going to be able to help us identify it when we observe it in the future. Bill, do you want to do a reflection?
I don't know. Yes, I mean, we can. I'm looking at some of the chat. I don't think we can take the time. Somebody asked about a quick demonstration to create the driver. I'm not sure that would be appropriate this evening. Dennis has given a partial answer here. They're not real advanced techniques. If we have some time at the end, we might be able to demonstrate that, but I don't think we want to do that at this point.
I noticed that Jeff had asked that question about using a circle instead of an angle, and the answer is I can certainly do that for him. I can certainly give him a set. If he sent me an email, I would definitely send him the way of descriptions for doing that creation.
And no, it's not done through the script editor. It's not nearly that fancy. So as Steve said, Mike, if you want to share our emails at some point, or you can contact Mike, we can get those answers to you. But looking here, as Steve said, as we look at the pre-image and the image, this appears to be a little bit differently. As we travel around the pre-image here, A, C, B, in a counterclockwise direction, A, C, B, and now we move to the image triangle and we travel in that counterclockwise direction. It's A prime, B prime, C prime. So here the orientation is opposite. So in this case, not one of the transformations that we looked at in our defining transformation activity previous to this. But as Steve mentioned, that activity did continue and includes this idea of the reflection. Lots of things to investigate here. So we now have opposite orientation. What's true, will we connect a pre-image to its image here? What's true about that line of reflection? So this is a different transformation from the ones that we have looked at so far.
How about we ask the question of fixed points? Just put a point P in the plane, or put a point in the plane, not on the line, and reflect it. Yeah, it's off the screen. There you go. Now just kind of drag P around a little bit, Bill. Would you do that for me? Once you've labeled it. One of the questions we're asking about in addition to orientation is, are there any fixed points?
I can't help but do something like this manipulation, Steve, and think of a quote that I would give credit to El Coco for about dynamic geometry being a vitamin for Euclid, which it truly is, but talking about the idea of continuity of argument, you know, if P is on one side of that line at some point and its image is on the other, at some point they must have both been on that line together, seems like. And if P were on that line, I think we have more than one fixed point in this transformation.
How about the question about parallel line segments? Is AB parallel to A prime B prime? Is AC parallel to A prime C prime? Those are questions that allow us to further identify this opposite isometry. Now, Bill, let's quickly turn to that last one because we want to get to the proofs. All right, now everyone should look at this, and let's look at the questions that we've just been talking about and see what we can do to identify this. Is it direct or is it opposite? Is this transformation direct or opposite? I see chat from Dan and a chat from Lee that say it's opposite because the orientation changes. Now, think about the ones we've talked about up till this point. Translation was direct. The rotation was direct. A reflection was opposite. Which one of those is this one? Well, we know it's not a translation because it's opposite. We know it's not a rotation because it's opposite.
Fernando says it's both.
Okay, it's both. Okay, I'm seeing some chat come through with a combination of both, but it's clearly none of the other three. It's clearly none of the other three. And this is the missing piece to our puzzle. This is the orphan of the translations. This is the one that doesn't have its own tool because, as many people said, it's a combination. If you turn the page, this is our little friend called a glide reflection. And a glide reflection, by definition, is a reflection over a line followed by a translation through a vector parallel. Now, there's lots of great investigations to do with glide reflections, all right? But we don't need a specific tool to produce a glide reflection because it's a combination of two of the other ones. This is the second of the two opposite isometries. So it's like a reflection in that it's opposite, but it's different than a reflection in that there are no fixed points. And of course, if we had the time to get the investigation, I'd say, how do you know there's no fixed points? Well, we could do a point and try it, or we could say, wait a minute, that translation down there moved everybody. All right, and that'll be how we identify. So we got 4 basic isometries, and we have the properties that are sufficient to identify all 4 of them. Now, Bill, I think we only got a few minutes left, so we need to go to the proofs.
Okay. And just quickly to respond to Leah, I can only respond from my experience. How easy is it for students to pick up on what to do in a file like this? My experience says it's very easy provided they have been in this environment on a regular basis. And I guess for me that means a daily basis. I could not imagine teaching geometry without some sort of interactive software. Believe me, I don't think it would be rocket science in many cases. So let's look at this idea of proof and using transformation with proof. We're going to look at a figure here where we're going to have a segment AB congruent to segment BD, BC congruent to BE, and DE is perpendicular to AB. I'm sorry, DB is perpendicular to AE at B. Our goal is to prove triangle ABC is congruent to triangle DBE. So here's our figure. Hopefully it's obvious that we can switch back and forth if we need to. We could group these pages if we want to. The problem with that is it makes the diagram very small. But we have AB congruent to BD, and we have BC congruent to BE, and DB is perpendicular to AE. Well, let's look at orientation first. A, B, C. Seems to be oriented in a clockwise rotation. What about D, B, E? Also seems to be clockwise. So we should be looking for a transformation which is direct. Translation or rotation. Any fixed points? B is its own image. B maps to itself, so it is a fixed point. Transformation has no fixed points. Sorry, translation has no fixed points. So I think we're looking at a rotation. We were told that BD is perpendicular. A 90-degree rotation would seem appropriate about angle ABD. So let's try our transformation. Let's rotate triangle ABC about point B. And now you may be saying to yourself, wait a minute, when we've used this tool before, we had that little driver up here for our angle. I don't have that now. I can just come out here in white space and say, oh, I want the angle to be 90 degrees. And do you see that dark triangle there? That rotation took place. As Steve mentioned earlier, if I now hover over this, I really have two triangles here. There is the rotated triangle, not named, and there's triangle BDE, which it ended up on top of. So indeed, it appears that this rotation about B of 90 degrees is the rotation that would superimpose triangle ABC onto triangle BDE.
We'd like to make the note now that this is the first step in a transformational proof in geometry. There's two parts to a transformational proof. The first one is to identify, because congruence is redefined under transformational geometry. Two figures are congruent if and only if one is the image of another under a rigid motion or under an isometry. We've discovered that it appears as though a rotation about B of 90 degrees maps triangle ABC to triangle DBE. The finished part, which probably will not be assessed in the Common Core standards, is to prove that what you just showed what you showed happen actually does happen. Bill, we got time to make just one quick look at this next one, and we'll have to shut down. We have a parallelogram, and in this particular problem, there's information given, but we're asked to show that line segment JN is congruent to line segment LQ. Now, traditionally in a synthetic high school geometry class, we would show that by finding two congruent triangles and using the corresponding parts of congruent triangles theorem. All right, in this case, we're going to show they're congruent by showing that there is an isometry that maps one onto the other. Now we're going to use the same discussion that we just did in identifying transformation. Obviously, line segments don't have orientation. So let's pick two triangles which have those as corresponding parts. JPN and LPQ look like triangles that may be congruent. So if we talk about JPN, that's clockwise, and JPN is clockwise, and LPQ is clockwise. So it's direct, and therefore it's either a translation or a rotation. But with those two triangles, P maps to itself. That's a fixed point. Translations don't have fixed points, so it's got to be a rotation. I know it's a rotation, and I know it's a rotation about P. What angle do we rotate? Well, J has to go to L. N has to go to Q. But more importantly, we observed when we were doing the rotations that the only time a line segment maps to a parallel line segment under a rotation is when the rotation is 180 degrees. So I think it's a 180-degree rotation about P. So if we rotate triangle JPN about P through 180 degrees, hopefully we'll get what we want. Did you see that happen? Again, all we really rotated was the segment, because the definition of congruence under transformations is two segments are congruent if and only if there's a rigid motion that maps one to the other. Again, the first step in a proof using transformations. Mike, I think we ran over.
Yeah, that's okay. We can't rotate in a different color, but we can change the color once we've rotated it. So I've changed the attribute of that image and the rotation to red dotted. So the LQ is behind it. The red dotted segment is the rotated JN.
And I'd like to remind the people that are listening, when you receive the materials, those materials will include a student worksheet. They'll include this TNS file, but they'll also include a set of teacher notes which really fills in all the explanations that we've been doing verbally during this discussion.